All right, homework out. Books open to page 264 to 265. You answered questions 6 through 8, 10, and 11. Also did problems 2 and 4 on page 265. As we began looking at sound, question number 6 asks this: what happens to the wavelength of sound ahead of a moving source and to the rear of the moving source? Kendall, what'd you have for number 6?
The wavelength of sound ahead of a moving source will get closer and louder to the person, and then to the rear it will just start to fade out.
It's talking about more the volume of the sound than the wavelength of the sound. Michael, what did you have for 6?
The wavelength of sound ahead of the source is compressed, and behind it is refracted.
Good, or some more spread outward. There we go. Number 7. How does the observed frequency of sound compare to its generated frequency when the source of waves is moving away from an observer and then toward an observer? Let's go back to Kendall for 7.
The observed frequency of sound compares to its generated frequency when the source of waves is moving away from the observer. It is reduced, and toward the observer it is elevated.
There we go. So as the source moves away, the frequency drops, and as the source moves toward, the frequency rises. Number 8, how does the apparent frequency of sound compare to its actual frequency when the observer is moving toward the source and away from the source? Audrey?
The frequency of the ambulance away from the observer is negative, and the frequency of the ambulance toward the observer is positive.
That's the velocities are positive and negative as the ambulance goes toward or away. Let's see, Michael, what did you have for number 8?
For number 8, if a person moves towards the source, it has a higher pitch, and as he moves away, it is lower.
There we go. Higher frequency, which frequency, pitch, we're going to get to that later. They're pretty much the same thing. So as the observer moves toward the source, there's an apparently higher frequency. As the observer moves away from the source, there's an apparently lower frequency. Number 10, how does a shock wave differ from ordinary sound? Audrey?
A shock wave differs from ordinary sound because it overtaxes the elastic properties of air by throwing large displacements into air molecules, and it basically travels above the normal speed of sound.
Okay, I'll take that. Number 11, what sort of waves are produced after an airplane has broken the sound barrier, and what is heard at ground level? What did you have for this, Kendall?
The waves produced after an airplane has broken the sound barrier are shock waves, and the sound that is heard on ground level is a sonic boom.
There we go. All right, good. We'll get into that today and tomorrow. Some of that today, some of that tomorrow. Let's review some things before we look at the problems. We began looking yesterday at sound, and we said, what is sound? Class?
A longitudinal wave.
It's a longitudinal wave. Good. Travels through elastic medium. And more specifically, which dimension is sound? 3-dimensional. So it's a 3-dimensional longitudinal wave that can travel through elastic media, which basically means that the only medium through which sound cannot travel is, I say medium, vacuum. And vacuum's not even a medium, right? So pretty much as long as there is a medium there is some degree of elasticity. There is some ability of sound to travel. Though obviously soundproofing uses materials that have incredibly low elasticity. Foam, for instance, has a very low elasticity. So there are things you can do to soundproof, but really the only medium through which sound cannot travel at all, period, full stop, would be a vacuum. We said that sound travels at different speeds depending on what it's traveling through, right? Depending on the medium, sound travels at varying speeds. There were 3 factors that affect the speed of sound. Audrey, give me one of them.
Hardness.
Hardness. Did we say hardness was a positive factor or a negative factor? Positive factor, meaning that if you increase the hardness, or if you have a substance with an increased hardness, the sound class will travel faster. Sound will travel faster if a medium is harder. A second factor that affects the speed of sound. Kendall? Density. Did we say that was a positive factor or a negative factor? Negative factor. So class, the denser a medium is, the slower the sound is going to travel through that medium. And the final factor that we said especially applies to gases, temperature. Positive factor or negative factor?
Positive.
So class, the warmer a medium is, particularly the warmer a gas is,
Faster.
the faster sound will travel through. In fact, we had an equation that shows how fast sound travels through air, and we can calculate it based on the temperature. What was that formula, Audrey? We started with V sub air, meaning the speed of sound in air. Not the speed of air, but the speed of sound through air.
331.5 meters per second times the square root of T sub C plus 273 all over 273.
There we go. As we account for the temperature, we can't have a square root of a negative. So since there's a square root relationship, we're going to convert the Celsius into Kelvin to get the absolute temperature. Compare that absolute temperature relative to 0 Celsius, which is the temperature at which this speed is valid. Take the square root of all of that, multiply by the speed of sound in air at 0 degrees Celsius, and that'll give us how fast sound can travel at that speed. There was one other equation we used yesterday, but it wasn't a new equation, Kendall. It was an old equation from the last chapter. And we got to see some things there with differing frequencies. What is the wavelength going to be of the sound waves? And a couple things that we derived from that. Not going to use that equation a whole lot in this chapter, but it's still an equation that's valid because sound is a wave. And some equations that related to waves before are still going to be in effect. Let's take a look then at problems 2 and 4 on page 265. Number 2, calculate the velocity of sound in air when the temperature is 30 degrees Celsius. What do we have to do first of all, Michael?
You have to use your formula, which is 331.5 times the square root of 30 plus 273 over 270.
There we go. Just plug the 30 in here for the T sub C. So add the 30 plus 273, divide 273, take the square root, multiply by 331.5. What did you get for that speed?
349.23.
Good, and then round it off to just 2 sig figs will approximate
350 meters per second.
how many? 350 meters per second. Great job. Excellent. Number 4, find velocity of sound in air in meters per second for air at 77 degrees Fahrenheit. This would be a warm winter day here in Georgia. It didn't quite get that warm yesterday, but it felt that warm at times out at P, didn't it, Audrey? It was pretty warm yesterday. So on a warm, maybe spring days, and then that's kind of morning temperatures in the summertime. Get up in the morning, it's already about there. Anyway, 77 degrees Fahrenheit. What do we have to do this time, Audrey?
I converted to Celsius and then to Kelvin.
Good. Convert the Fahrenheit to Celsius first, and then convert it to the Kelvin to divide by the 273. What did you get for the Celsius temperature, first of all?
170 and 3/5.
77 Fahrenheit? I think we might have used the wrong equation. To find Celsius, remember Celsius is going to be the smaller numbers generally. So we need to take the smaller fraction. Which is the smaller, 9/5 or 5/9? 5/9. So we're going to go with the smaller fraction, and then also we're going to make the number smaller right off the bat by subtracting, not adding the 32. I think you went the wrong direction. So yeah, should have taken the 32 away first to make it smaller, then take 5/9, which is the smaller fraction. So if you just think small, right, Kendall? Think small, and you'll end up with the Celsius temperature. So she's redoing this, and what should the Celsius temperature be at 77 Fahrenheit?
25.
There we go. So 77 degrees Fahrenheit should have converted to 25 degrees Celsius. That's what we'll plug in here. And so go ahead and re-enter that. So again, always remember Celsius is, generally speaking, a smaller number than Fahrenheit. And
346.3.
good, 346.34, blah, blah, blah. And round it off to, again, 2 sig figs.
350.
This also comes to 350. Even though it's not quite the same temperature, it was close enough to the last one, 25 degrees Celsius, 30 degrees Celsius. They were close enough that the temperatures rounded the same. How many had 350 degrees Fahrenheit? By the way, if you want to jot this down, this is a number I actually have memorized because this is a pretty standard temperature. I mean, you can hit this temperature just about anywhere in the U.S. So 25 degrees Celsius is 346.346. To me, that's an easy number to remember because it repeats itself. Now, it's blah, blah, blah. Okay, it's not exactly that. But if you wanted to kind of tuck this number in your memory, 346.346, might help us because there's going to be a number of problems later on where we're going to say, well, let's assume it's 25 degrees Celsius outside. So since I know what's coming, it might not be a bad number to memorize. How many had that, though, for number 4? All right. And then Audrey, just careful with the Fahrenheit Celsius conversion. All right, flip back in your books if you would now to page 255. Page 255. There's a picture of a boat moving very slowly through the water. And I know it's moving slowly. How many have ever been in a boat, kayak, canoe, any type of watercraft? You know you don't have to move very fast for what's called a bow shock to develop. So for instance, you're in the kayak and the waves kind of just come off the front edge of the boat. You know what I'm talking about? Okay, you would have to go very, very, very slowly for waves to actually ripple in front of you in a way that you can see, admittedly. Because water waves, as a rule, move very slowly, right? You drop a rock, the ripple doesn't race outward. The ripple slowly moves outward, correct? Sound waves aren't like that, though. Sound waves move very, very quickly. So although we're going to use water waves to visually picture this, we understand that everything has to slow down because water waves, as a general rule, move slowly. If we drop a rock into the water, we get a perfect circular ripple effect that comes outward. But imagine if when we didn't just drop the rock, we sort of dragged the rock slowly. The rock, as it's creating the ripples, would put the ripples outward, but if it were moving slowly this direction, it would push this first ripple into the second, and the second into the third, and the third into the fourth, kind of like what you see on that first picture at the top of page 255. We see a boat very slowly moving forward, exaggerated ripple effect, but we see how in front of the boat, the ripples of the water, or the wave fronts, are compressed slightly. Does that make sense? The wave length, then, is reduced. Does that make sense? Ahead of that moving boat, the wave length is reduced a little bit, and therefore, the waves hit more quickly, don't they? The frequency increases because the speed of the waves is predetermined by the medium, the depth of the water, the type of water, all that kind of thing. Now, as the boat sits there in a river, if the boat were to sit still and the current were to move against the boat, we'd see a similar effect take place. We would again see those wave fronts compressed in front of the boat. Again, it's going to be really hard not to just produce that shock wave, if you will, off the front edge of the boat, or that main bow wave. But in theory, if the current were slow enough and you had a little bit of wave action, you would get that compressed feel. That's going to be true of water waves, but it's going to be true of sound waves as well. As I'm speaking, right, 3-dimensional longitudinal waves coming out of my mouth, but if I were to be walking forward, my own movement would take those wave fronts, those compressions and rarefactions, and push them slightly, ever so slightly, closer together. On the back end, we would see, if we could see the sound waves, we would get something very similar to what you see, where the wave fronts would be slightly exaggerated. The distance between compressions would be just a little bit greater. Does that make sense? Now, not enough for you to notice if I'm just walking. And frankly, even if I were running at top speed, you probably wouldn't notice much. Okay? I know because I was weird when I was in high school. I don't know that I was thinking Doppler effect, but I don't know. But it's my first day of track practice, so I was a senior at this point. So, I wasn't like the scared little kid who's out there at track practice, like, what's going on? I was a senior. I was a captain on the cross-country team. I was confident in my abilities and my racing ability. So anyway, we're jogging this first warm-up lap of the season, and I just decided to be stupid because high school boys are stupid. We do stupid things sometimes. Anyway, so I'm jogging the warm-up lap, and then I get to the last straightaway. I'm like, I'm just going to sprint all out, just scream my head off while I do it. I don't know why I thought that was a good idea. I cramped my neck up, though. All my neck muscles locked up right there when I started screaming, and it was very, very painful and awkward. Anyway, but imagining, though, okay, flashback, if you can even visualize this, Mr. Nasky being stupid, racing at top speed down the straightaway, screaming his head off. There is a certain frequency of screamage coming out of my mouth, right? But as I'm racing towards you, I'm pushing the wave forward, right? If I just stood still and screamed, the wave would go forth, right? But if I'm racing, I push the wave faster, which pushes wave fronts together a little bit. Again, as that wavelength decreases, since the wave speed has to stay the same, sound is going to travel the same in that medium regardless. Since wave speed stays the same, if the wavelength is shortened, remembering that v equals lambda f, lambda goes down. To keep a constant speed of wave, what has to happen to the frequency? It's got to go up. Again, look in front of the boat. Where you see shorter wavelength, you see more waves per area, correct? More waves per second, if you will, higher frequency. So in theory, as I'm sprinting down the track, I'm emitting one frequency, you would hear a slightly higher frequency. Does that make sense? Behind me, there is an actual frequency I'm emitting, but on the back end, because I'm moving forward, I'm kind of pushing everything forward. On the back end then, again, we get the effect that's pictured there, exaggerated, longer wavelengths. Well, if the wavelength increases to maintain equal speed, what has to happen to the frequency? Decrease. And where you see behind the boat the longer wavelengths, you also see a lower frequency. There are not as many waves per area, so to speak. Does that make sense? That's what we call the Doppler effect. Now, this has nothing to do with Doppler radar, just in case you're like, I've heard of Doppler before. No, it's not the same thing. Okay, Doppler effect in relation to wave movement. Here's my definition. The Doppler effect is the shift in wavelength and frequency. The shift in wavelength and frequency of waves. The shift in wavelength and frequency of waves. The shift in wavelength and frequency of waves due to motion of the source or observer. The shift in wavelength and frequency of waves due to motion of the source or the observer. The shift in wavelength and frequency of waves due to motion of the source or the observer. So what I gave you in the last example was, imagine I'm racing down the track screaming my head off, being stupid. Okay, you're going to hear a slightly higher frequency as I'm coming towards you, but if you were behind me, you'd hear a lower frequency. The same would be true if I were standing still screaming my head off, and Kendall, being the compassionate, kind-hearted soul that she is, she's like, Mr. Nadesky's screaming. I wonder what's wrong. Michael's rolling on the floor laughing. Audrey's very confused, and Kendall comes rushing to my aid. Thank you, Kendall. Appreciate that. Well, as she comes racing to my aid, as I'm screaming, because of her movement, again, as I'm laying here on the ground, screaming my head off, okay, wave fronts are coming out at regular intervals. But if she's racing toward me, she's going to hit them more rapidly than if she stood still. Does that make sense? So what she's going to perceive, there is no increased frequency if I'm still, but because she'll hit these wave fronts quicker moving toward me, that she will perceive a greater frequency because she hits them more frequently. Does that make sense? And that's why I said the motion of source or the observer. Now, if it's Michael and he's standing there right next to me when I don't know what happens to me that I'm laying on the ground screaming, but Michael's right there and he's like, I'm getting out of here. And so Michael takes off running. Okay, well, as he's running away from the wave fronts, so to speak. So because he's trying to get away from them, he'll be hitting them, they'll be reaching him, I should say, more slowly. He's trying to outrun them. They will reach him because sound is faster than Michael can travel, okay? He may be fast, but he's not that fast. Sound is still faster, but they won't reach him as quickly because he's going away. So in his case, he will hear a lower frequency. Here's the basic rule of thumb, and it's true whether you're the observer or whether you're the source. When two objects approach, whether it's the source approaching the person who's listening, whether it's the person listening approaching the source, or both, when you approach, the frequency goes up and the wavelength goes down. Not the actual frequency and wavelength necessarily, but that which is perceived. And when objects depart or go away from each other, the perception is that the frequency decreases and the wavelength increases. Again, this is true whether you're the observer or whether you are the source. Now, question. I said this before. If I were just walking towards you talking, technically there will be a slight increase because as I walk, there's a slight compression of wavelengths, right? Wave fronts. But, I mean, really, truly, sound is traveling at 340 something meters per second. Me walking towards you at 1 meter per second does nothing, right? Even me sprinting at top speed at about 15, 16 miles an hour, that might compress the waves a little bit. But even more so if I were in a convertible driving towards you. Maybe it's an electric convertible, EV, right? Electric vehicle, so that we don't hear all the motor noise. And I'm like sitting there in my convertible screaming my head off as I drive towards you at, say, 60 miles an hour. Well, now all of a sudden you're going to get a much more pronounced effect because I'm traveling that much faster. Does that make sense? The faster the object moves towards something, the greater the impact. Or as it goes away, the faster it goes away, the greater the effect is going to be. So just note the effect is most pronounced as speeds increase. This effect is most pronounced as speeds increase. The effect is most pronounced as speeds increase. So then, it makes sense, does it not, that the Doppler effect is going to hinge largely on speed. How fast are the objects moving? The object making the sound, whether it's an ambulance, whether it's a train, whether it's a Mr. Nadasky screaming his head off. And I know those of you watching on YouTube are like, he's such a dignified man. I mean, I can't even imagine him screaming his head off. Right? You all would agree with that assessment? Just very dignified. Anyway, but anyway, whatever the object is that's creating the noise, right? As its speed increases, as the person observing. Maybe Kendall's also in an electric vehicle and she's going the other way, racing toward each other on the road. Well, if she's also in a car racing at 60 miles an hour, I'm racing 60 miles an hour going the other way, then you're going to get an even more pronounced effect, right? As speeds increase, you're going to get a greater, more pronounced Doppler effect. And here's the equation. F sub O, meaning the frequency that is observed, the frequency the observer hears, is going to equal the frequency the source emits if there were no motion, correct? I'm standing still, you're sitting still, I'm talking. The frequency that comes out of my vocal cords is the frequency you hear. But let's suppose there's movement. Well, again, it's all relative to how fast sound is already traveling, right? The fact that sound already travels at this speed, at 0 degrees Celsius at least, I mean, depending on whatever the temperature is, sound's traveling maybe this speed, right, whatever. The speed that sound travels at, but that's affected then by the additional speed of the moving object. So we would say, we have this fraction. The speed of sound in the air, whatever that speed is, plus the velocity that the observer is moving toward the source. And we're going to divide that by the speed of sound in air minus the speed of the source that is emitting the sound. So F sub O, the frequency of the observer, equals F sub S, the frequency the source actually emits, times, and we're going to make this ratio to compare the speeds at which the object is traveling. And again, that's going to be affected by, of course, the speed that sound would travel in air already. V sub air plus V sub O over V sub air minus V sub S. Now, there's a lot of subnotation, and there's a lot to keep track of. So let me help you out a little bit here. Think alphabet. O comes before S, O comes before S. That'll help you keep which one straight, right? OS, OS. Also, we always say positive, negative with square roots and stuff, right? Positive, negative. So if you think logical alphabetical order, logical positive, negative order, that should help you keep straight what goes where. Now, the next issue is this, because velocity has direction to it, correct? Not just speed, but direction. Well, it depends on the direction. If the objects are approaching, speeds are positive. If both objects are approaching, both speeds are positive. But in general, these V's, the V sub O and the V sub S, they'll be positive if the one object is approaching the other. The velocity will be a negative velocity if the objects are departing each other, or if one object is departing the other. So for instance, we have Michael and we have Kendall. If Kendall is going toward Michael, is Kendall's velocity positive or negative, class? She's positive. What if Michael's going away from Kendall? Is Michael positive or negative? He is negative, but she is still positive because she is still going toward him. Let's suppose they're both running full speed. I'm sorry, Kendall. I should have more faith in your sprinting speed. I got a feeling with his longer legs, he's got an advantage. He may actually be leaving her behind. But because she is still approaching toward him, even if he's leaving her in the dust, she's still got a positive velocity. Make sense? Now, what if Michael's coming toward her? Now Kendall is
Getting out of the way.
getting out of the way, so you're saying it's true, but Kendall is still positive, and Michael is now also positive. So it's possible for both to be positive. It could be Kendall looks at Michael, Michael looks at Kendall, they both run away. All right, well, okay. Kendall, I understand. Anyway, but if they're running away from each other, now they're both going to be negative. And maybe Michael's like, wait a second. And Michael turns, hey, Kendall, wait, it was just a mask I had on. I don't know, it's whatever scary mask. It's got to be the mask. Anyway, well, now Kendall class is negative and Michael is positive, right? So each individual object, it doesn't have to be they're both approaching or both departing or what the net result is or anything like that, right? If Michael were actually trying to chase down Kendall, he would catch Kendall, okay? He is faster. Now, you know, depending where Dad is with his shotgun, whatever. But anyway, if Michael were chasing after her, he would catch her, but she is still negative because she's running in the opposite direction away. Does that make sense? So each object that emits the source, or the object that is observing the sound, and the object that is the source of the sound, each one you have to think, is this positive or negative? Okay, for the next object, is this positive or negative? Because up here, if you add a positive, it's positive. You add a negative, okay, that's going to produce a smaller number. Down here in the bottom, if you subtract a positive, okay, that gives you a smaller number. You subtract a negative class, that becomes positive. Does that make sense on the algebra of that? All right, let's look at some example problems. So I think by practicing this, we will have a good idea here. Again, you see at the top of page 256 now. By the way, page 256 on the side there, equation 4 is your Doppler effect equation. I added V sub air, and I also added the parentheses to the equation. Parentheses, to help us remember, this is all got to be figured out first. V sub air, meaning that's what the V is. It's however fast the sound would be traveling in air already. Alluding to, we're going to need to use this equation potentially again. At the top of the page, they have, again, they almost imply if they're both going, it's positive. If they're both going away, it's negative. Well, that's true, but they could be going in the same direction where one's positive and one's negative as well. So I want to make sure I mentioned that. Example 17.3 now. Go ahead and read that if you would, Audrey.
You are standing in a railroad crossing while a train approaches at 15 meters per second. The locomotive blows its whistle as it is passing by. What frequency do you hear as the train arrives and as the train departs? The whistle emits sound. Raise that of frequency of 340 hertz. Assume the air is at 25 degrees Celsius.
All right, so how many have ever been at the train station? You've heard what I'm talking about, the train, and you kind of hear that drop off in the tone. And that's the Doppler effect. What you were hearing was actually an elevated frequency. It wasn't the real frequency anyway. And after it passed, you heard a depressed frequency, so you noticed a bigger gap. And the true frequency was actually right in the middle of what you heard. So that's what we've got going here. You're standing there waiting. Train's coming 15 meters per second. Don't run to beat a moving train. That's not smart. And so the locomotive comes on by. All right. The first thing we want to do here is we're finding the observed frequency, the frequency that you as the observer hear, is to plug in the frequency that the source actually emits. If the train were sitting still and you were standing still, you would hear what frequency, class? 340 hertz, because that's the frequency that the train whistle actually makes. But that's not necessarily the frequency that you hear. We need to plug in, first of all, the V sub air. And notice what temperature it says the air is. 25. Now, if you look at their work, you'll notice they just plugged in 346 as opposed to 346.346. I'm cool with that too. In fact, if you look back a few pages, back on page 253, you'll notice they actually have air at 0 and air at 25 on the table for you. That's where they pulled the 346 from. Now, if you wanted really exact, is the 0.346 going to make that much of a difference? Probably not. And then they add the speed of the observer. Well, you're the observer in the problem, and it says you are doing what class? Standing. So what's your speed? What's your speed? 0. Your speed is 0. So the numerator is just going to be the 346, right? In the denominator, we're going to subtract the speed of the train. Now, it says, first of all, the train is approaching you. If the train is approaching, is its speed positive or negative? Positive. So we're going to subtract a positive 15, or just subtract 15. 346 minus 15, of course, is
339.
331. 346 plus 0 is, of course, 346. So we're going to divide and figure this whole thing out first. 346 over 331 should give you 1 point something.
1.045.
1.04, blah, blah, blah. That value gets multiplied by the 340 hertz to tell you what frequency you will actually hear. 355.4, blah, blah, blah. And is it 366, I hope?
2.
Rats. So we have to round up to
360.
360. That makes it sound like there's a bigger difference than there really is. By the way, we're going to get to this at the end of the chapter. An octave is a doubled frequency. So if to hear a full octave higher, you'd have to hear 680 hertz. Okay? Half an octave then would be approximately half of that change, right? We're not, 15, 20 hertz difference, that's not a huge difference. You're maybe hearing, you know what I'm talking about when I say a half step. That's maybe about all you're hearing is maybe a half step difference here. That's not that much. But it's a little something higher than what you should be hearing. 355, where we had to round to 360 hertz. But then the train goes by, right? And now you're still standing still, but now the train class is leaving you. So the velocity of the train now becomes negative 15, and it's minus negative. Well, that's going to have the result of adding the positive 15 to get what new denominator class?
361.
361?
Yeah.
So now we're going to have to divide 349 by 361. I think that gives you 0.9 something. 0.95, blah, blah, blah. Okay, multiply that by the 340 hertz. And after the train has passed you, what frequency are you hearing? 325.87, blah, blah, blah. Okay, round it off. Again, only 2 sig figs, so we'll round to 330 hertz. Again, that's not a huge drop. That's maybe a half a step drop from what's actually emitted to what you hear. But from what you hear initially to what you hear after it passes is about a whole step drop. About one note. So, okay, about one step drop is about what you're hearing there for this particular train whistle at that particular. That's kind of a lower frequency, actually, so that's not a super high frequency there. Questions on this? Do we see how to plug the numbers in? Again, the nice thing about this example was you were standing still. So that made the numerator a little bit easier. Look at the next page. And example 17.4, read that for us if you would, Kendall.
Suppose you are driving east at 32 meters per second and an ambulance traveling west approaches at 53 meters per second. If the frequency of the siren is 620 hertz, what frequency do you hear A as the ambulance is coming towards you and B after it moves past? C, what frequency do you hear if you turn around and follow the ambulance at 32 meters per second? D, what frequency do you hear instead if the ambulance turns around and follows you in your original direction at 53 meters per second? Assume the error is at 25 degrees Celsius.
All right, so we got all 4 different ways you can work the problem. So I love this example here. For one thing, the frequency is a little bit higher. Now again, we know that a real ambulance makes the pitch is constantly changing, the frequency is constantly changing. So we're going to assume that his wooer got stuck, and it's only woo as it goes along. Okay, so it's kind of like the siren thingy. You know what I'm talking about, the tornado drill siren. Okay, we're just assuming it's stuck on that one note. For some reason, it's just going down, woo, going down the road, okay? And so that particular frequency it got stuck at was 620 hertz. That's the frequency of the source. So 620 hertz is where we start off. Now, once again, it says it's how cold outside or how warm outside, class? 25 degrees Celsius, which means the speed of sound in air is not 331.5, but we'll assume 346. And that goes in, obviously, for both of those. Now, in the original problem, it says you're driving east, so this is you, and then the ambulance, it says, is going west, approaching you. So you're driving on one side of the divided highway, hopefully, not on a one-lane street. Okay, it's on the other side of the divided highway, because otherwise you'd be pulling over right now, right? A divided highway, we all know that from driving. Okay, divided highway, you can keep going. Not divided highway, you have to pull off to the side for emergency vehicles. And this is the ambulance. And you're going at a good clip. You're going about 65 miles an hour, 32 meters per second. The ambulance, though, I mean, this is life or death. donut sign is that's plates. Anyway, so it's life or death. They're racing. They're 53 meters per second. So I mean, they're up around 110 miles an hour. They are really booking it down this highway. We've got a very high speed difference here, don't we? So we're going to get a very pronounced Doppler effect. But notice both objects, you and ambulance, are approaching. So both velocities, class, are positive. So your velocity, the velocity of the observer, is positive. And the velocity of the source is also positive. And of course, that positive gets added, this positive gets subtracted. So in the numerator, what's our number going to be? 378. And in the denominator, our number is going to be 293. We're going to divide that and then multiply by 620 hertz. What do we get? 709? 799? 799.8, blah, blah, blah. Even if it's 3 sig figs, we're still writing the same thing, aren't we? And, it's 2 sig figs. Man, so what do we get?
8.0.
Not 800, but 8.0 E2 hertz. That's annoying. Come on, give me 3 sig figs, folks. All right, so that's what we hear as the ambulance is racing towards you. It's actually going, woo, and you hear, woo, okay? And then, woo, it passes you. Now, you're going this way. Now the ambulance is going this way. All right? Now, all of a sudden, both you and the ambulance class have negative velocities. So this becomes a negative 32. Well, add a 346 plus a negative 32. 314. And this is a negative 53, but it's minus a negative, which means we have to add the 53 to get 399. And so we're dividing 314 by 399, multiply whatever that is to 620. And so we hear, it's actually only doing 620, but we hear 800. And then after it passes, it drops all the way down to
487.9.
487.9, rounded off. This one's not as bad. 490 hertz. Almost, I mean, cut it in half would have been 400, so it's not quite a full octave drop. But I mean, that's several steps lower if it were stuck at that pitch and you were both going that fast. Okay? So that's a big, big time drop. Now, the next question is kind of interesting. Because remember, the ambulance is racing towards you. Ooh, it goes past. Ambulance now going this way, still 53 meters per second. And you're like, wonder where he's going. Turn around, and now you're following the ambulance like, I wonder where he's going. I wonder what happened. Was it somebody I knew? So now you are going this way. That was part C. You turn around and follow the ambulance. Well, who's positive and who's negative here, class? Ambulance is trying to get away. It's negative. You're chasing the ambulance, so you're positive. So this is now a positive 32 because you're following after the ambulance. You're going toward it. Now it's getting away from you, but you are going in the direction toward it. So it's a positive 32, which means we're back to what in the top? 378, which is what we had originally. But the bottom is still negative 53. So negative, still 399 here. So if you follow the ambulance, now do the math. What is it, 587? Ooh. 587.3. Doesn't really matter because we're only rounding 2 sig figs anyway, right? We get 590 hertz if we follow the ambulance. And the last one to me is my favorite because you're just driving along, ambulance like, ooh, wait a second, Kendall's an accident waiting to happen. Let's be there when she has it. And so they turn around, they start following you. That's not scary. All right, so remember, you were going along merrily on your way at 32 meters per second. Ambulance passes you and it's like, whoop, let me follow Kendall. And so ambulance now going 53 meters per second. Now who's positive, who's negative, class? Ambulance is positive, you're negative. All right, so this is now a negative 32 and this is now a positive 53. Well, what's the top going to be now, class? 314. And the bottom?
293.
All right, divide that out. And what do we get?
664.43.
664.4, blah, blah, blah. Rounded off, still just 2 sig figs. 660. The 4 doesn't quite bump it up. 660 hertz is the frequency you hear as the siren. Now, again, he's going to mow you down. At this point, you technically have to pull over anyway, but this is assuming you didn't know that rule, and so you're still going, at the same speed. And he comes up behind. He passes you, though, of course, eventually. But as he's coming up on you, that would be the frequency that you hear. Questions on the 4 different ways you could apply Doppler effect. All right, obviously, if one of the objects is stationary, that helps, right? Just plug in zeros. But 4 different ways in which you can plug in those different directions. Turn to page 265 now, if you would. We'll do one more of these together, and then we'll wrap it up. Page 265, and look at problem number 8. Page 265, problem 8, and Michael, read this one for us.
One summer, yes, you are driving down the road at 22 meters per second. You pass a car driving towards you at 16 meters per second. The air's temperature is 29 degrees Celsius, and you can hear the other cars hear you as the car is passing you. As the car is passing you, Pavarotti hits a sustained high C at exactly 528 hertz. What frequency do you hear as you approach the other car and as the other car passes?
All right, good old Pavarotti, the opera person. So he hits a sustained high C as they're passing you, and you have to listen to it. So what I would do is I'd say there's you, and there's Pavarotti. All right, starting off, class, you are driving 22 meters per second in a particular direction. Doesn't really matter. Pavarotti, he's coming towards you at 16 meters per second. Who's positive, who's negative? Both positive. All right, what's our equation that we're going to use to find Doppler effect here? Audrey?
F sub O equals F sub S times V sub air plus V sub O over V sub air minus V sub S.
Now there's one little detail. It says it's 29 degrees Celsius. We don't have that one memorized. So let's go to our equation. We'll add the 273, divide the 273, take the square root, multiply by 331.5. And what is our V sub air that we're going to need to use here?
348.66.
Let's just put that in the memory of the calculator, 348.66. That might make our life a little easier if we remember that this is just in memory 1. All right, so in the top, we're going to have M1 plus, class,
22.
you are the observer, plus 22. In the bottom, we're going to have M1 minus 16. So we have M1 on the calculator already, plus 22 equals, I'm going to say divided by, I'm going to do parentheses. So divided by parentheses, recall 1 minus 16, close parentheses, equals. I should get for this whole fraction a 1.114 blah, blah, blah. All right? Then multiply that. Now, what is the frequency of the source? What is Pavarotti actually hitting here? 528 hertz. So we just multiply by the 528 hertz. And what frequency do we hear? Ooh, 588.3. Is it 3 sig fixed this time? Nope. So we round it off and say approximately,
590.
we hear about 590 hertz. Okay? Questions on the first part of the problem. Then Pavarotti goes past us. You didn't know I could hit that note. We go past, Pavarotti races past us. Here's Pavarotti here. Still going 16 meters per second. Now who's positive, who's negative, class? Both negative. I like that note you hit was negative. Anyway, so both negative now. So we're plus a negative 22 and minus a negative 16, which means in the top, practically speaking, we need to take M1
Plus.
minus 22, right? So we do recall 1 minus 22 equals, I'm going to divide that by and use parentheses in the bottom, recall 1 plus 16. Close parentheses equals, my big old fraction thing, you should come out to a 0.8957 at this point. Multiply that by Pavarotti's 528. And after Pavarotti passes us, of course he's not actually the one driving, he's just on the radio, we hear, and round it off, that'll be, 470 Hertz. Questions on Doppler effect? Feel like we got it pretty well? All right. Homework is to practice a few more of these. I want you to reread over pages 255 to 259. So for homework, I need you to reread 255 to 259. On page 265, do problems 5 through 7. Page 265, do problems 5 through 7. Read 255 to 259. On page 265, do problems 5 through 7. We'll finish up this talk on the Doppler effect in our next lesson. Have a wonderful rest of your day. When the bell rings, you are dismissed.